In this video, we will be going over another stress transformation problem. As you can see, we are given the stress state at point A, and we're asked to find the principal normal stresses and the max shear stresses, including all of the angles and the stresses. We're also asked to find the rotated stress state when you rotate that stress block at point A 50 degrees counterclockwise, and then we're also asked to find what P1 and P2 are going to be on the beam. So this video is going to be broken up into two parts. The first part, solving the stress block, which is going to be the first three parts of this problem. And then the second video that I'm going to do is going to be solving that last part, solving for P1 and P2 on the beam. So let's get started. So the first thing we do, since we're given the stress state at point A, we can just go ahead and just draw our stress block at point A and then use that to make our coordinates for our Mohr circle. So here is what our stress block looks like from that given stress state. We only have a normal stress on our z plane because our sigma zz has a value of 238, so that's on the z face. We're going to have a value of 238 psi, and it's positive, so it's causing tension. And then we also see that we have a shear stress on both the sigma zx and xz planes, so that's what gives us the stress block right here. So now all we need to do is kind of create coordinates to be able to plot our Mohr circle. So we'll start with our x coordinate. So on the x face, the first term is the normal stress. There's no normal stress on the x plane, so that's just going to be 0. And then our second term is our shear stress on the x plane, which is going down and causing a counterclockwise rotation, or sorry, a clockwise rotation. So that's going to be a positive 40.2 psi. And then our z coordinate, it has a positive normal stress in the z direction, so that's going to be 238 psi. And then similarly, the positive z-axis face is going in the negative x direction, and it's causing a counterclockwise rotation, so that's going to give us a negative 40.2. So those are our 2 points that we're going to plot in order to plot our Mohr circle. So I'm just going to go down here and give us a little space so that we can draw that. So here is our plotted Mohr circle. So now what we're going to want to do is kind of define the circle a little bit more. We're going to want to find the center. And so the equation to find the center of our circles, and that since we have 2 of the points, that's just going to be equal to the first term in each of our sigma term, or our normal stress term, added together divided by 2, so the average of them. So one of them is 0, the other one is 238. That divided by 2 is going to give us a value of 119. So that's where our center is located. Next, we have to find our radius of our circle. So our radius is just going to be equal to, so if we look at it in terms of a triangle, our triangle is going to be this guy right here. So we can use our terms in order to find that. So our radius is going to be 40.2 squared, that's one of the sides, plus 119 squared, which is the location of our center. And so that's going to get us an R value that is going to be equal to 125.6. So now that we have those 2 things defining our circle, we can go ahead and find our max points. So our sigma max, sigma min, and also our tau max. So the first one, the easiest one, our tau max, that's just equal to our radius, so it's going to be equal to 125.6 psi. And then our sigma max, that's just going to be equal to our center, which is 119, plus our radius. So that's going to be plus 125.6. So that's going to give us a value of 244.6 psi. And then similarly, our sigma min is also going to be the center, but instead it's going to be minus our radius, so 125.6. That's going to give us a value of negative 6.6 psi. So now the next thing to find is just the rotations that have to happen in order to get those 2 values. So to find that rotation, we just need to find a certain angle. So this angle, we'll call it theta. We need to find that angle in order to find the 2 rotations needed to get the tau max and also the principal stresses. So if we were to draw what the principal stresses, we would need to rotate our line to this line right here. So that right there is going to be 2 theta p, because however much you rotate in the actual system on the Mohr circle, you're going to rotate double that. So that's going to be to find our principal stress, and then in order to find our angle at tau max, we need to rotate through this angle, which we're going to call 2 theta s. So first, let's find our pink theta. So that pink theta, the tangent of it, that's just going to be equal to 40.2 over 125.6, since we know with that. And excuse me there, I actually meant that's not the tangent, that's going to be the sine of theta is going to be equal to 40.2 over 125.6, which is the radius. So doing that, that gives us a theta that's going to be equal to 18.7 degrees. So now we just need to relate that theta to both of our 2 theta s and 2 theta p in order to find those two angles. So if we go back to black here, so we can obviously see that our pink theta, that's just going to be equal to whatever 2 theta p is equal to. So that gives us that theta p is just going to be equal to 9.4 degrees in the counterclockwise direction. And then we also can relate this theta. So theta, if you add the plus 90 degrees to it, you should get 2 theta s. So doing that, you can get that theta s is going to be equal to a 54.4 degrees counterclockwise. So now let's show the principal stresses and the max shear stress cases on a stress block. So I'm just going to draw those down in this space right here. So here are the stress blocks for both those cases. On the left, you can see we got our principal stress case where it's rotating a counterclockwise of 9.4 degrees, and then we get the max and min principal stresses on each of the faces. And then on the right, you can see this is the case that has the max shear stress. It's also going to have some normal stresses, but this is where you find the max shear stress on the stress block when it rotates 54.4 degrees counterclockwise. So the next thing we just got to do is we got to rotate our stress block from the original to 50 degrees counterclockwise, like the third problem statement says. So that's what we're going to do. We're going to have to redraw our Mohr circle and rotate it 50 degrees counterclockwise. So since we are rotating 50 degrees counterclockwise in our actual system, that means on our Mohr circle we're going to be rotating 100 degrees. So what that kind of looks like, so we'll say maybe it rotates right about there, and then we're going to go through our center here. So we'll say that this is our z prime and this is our x prime. So this is the new rotated state. It still goes to the same center, it's just got different stresses now. So now we're going to want to look at this triangle right here, the one that goes right here and then down. So we're saying that this has rotated 100 degrees. So this is the triangle that we're going to want to look at, this second purple triangle, in order to figure out what the stresses are going to be at the 2 points. So we'll just go down here and draw that triangle again. The first thing we got our triangle, the first thing we got to do is figure out what that angle theta 1 is. And if we look back to our Mohr's circle, you can kind of see that theta 1 is just going to be 100 degrees, which is what we rotated, minus that pink theta that we had originally solved for. So our theta 1 is just going to be equal to 100 degrees minus that theta 1, which is 18.7. So that's going to get us a value of 81.3 degrees. And so now through trigonometry, just using our sines and our cosines, you can figure out what L1 and L2 is going to be. So you know that the sine of theta 1 is just going to be L2 over R, and we know what R is, so we can get what L2 is. This gives us an L2 that is equal to 124.2. And similarly, the cosine of theta 1 can get us that L1 over R is going to give us an L1 that is equal to 19.0. So now that we have those two lengths, we basically know what the stresses are going to be at our x prime and our z prime state. So we can go ahead and use this and state what our coordinates are going to be. So our z prime coordinate, that is just going to be the center, which we know to be 119, plus our L1 term. And then our second coordinate, which is our shear stress, how high up it goes, that's just going to be the value of L2 since it's positive. So that's going to get us a value of 138 for our first term and 124.2 for our second term. So similarly, do the same thing for the x prime coordinate. This time, however, the first term is the center minus L1, and the second term is a negative L2. So doing that, you should get a value of 100 as your first term and a negative 124.2 as the second term. So now that we have those two, you can go kind of back calculate and figure out what the stress block looks like. So I'm going to draw that off to the right. So here is what our stress block looks like when it's rotated 50 degrees counterclockwise. We just plotted our z-coordinate and our x-coordinate on the stress block, what we got from our Mohr circle, and so this is what we get. We get 138 psi on our z prime face and 100 psi on our x prime face, both in the positive direction, causing tension. And then you have 125.2 psi on each face, but noting that on the x prime face it causes a counterclockwise rotation, which is denoted as negative. So that's kind of what states like the direction of all those arrows. So that's the conclusion of this first part. I'm going to make a second video that's going to finish up this problem with finding P1 and P2.